Welcome back to this open source chip design and verification event. Our next session will be on the topic of FPGAs in bringing code novelties using open source customized linting. This session is rendered by Mr. VP Sampath, founder of the Bharat Semiconductor Society, an FPGA expert. Sampath will explore how FPGA-based designs can benefit from customized linting solutions. His session will cover how tailored linting tools are being applied to FPGA workflows to enhance performance, uncover hidden issues, and streamline code development. At AsFigo, we recently joined Altera's ASAP program, which stands for Altera Solutions Acceleration Partner. Through this partnership, we are bringing FPGALint tailored to Altera devices, including the latest Agilex 7 series with AI function blocks. So tune in to this developing solution for FPGALint.
Giving opportunity AsFigo and Verifox. So I want to walk through some of the FPGAs for nearly 260 companies with different personalities from their different industries, also exceptionally esteemed institutions across the world. We have formed a community to make the ecosystem more stronger in the ESDM. Thank you very much for joining this event. My topic is FPGAs in bringing code novelties using open source customized linking. I joined with AsFigo Verifox to present this talk. Thank you very much for giving an opportunity to AsFigo and Verifox. So I want to walk through some of the FPGAs market to evince most interest for the audience too. The global market for the FPGA is about, the market is growing very widely and aggressively, 13.6%, and the forecast for marketing for the 2033 is $39 billion. FPGAs applications in high performance networking, 5G, and the research in 6G, and a quiet exploration in the automotive field, ADAS, and tight synchronization technique schedules in and alarming growth in the defense. FPGA proves a lot of competitive marketing today. So there are different types of FPGAs, as you know, that high performance FPGA, low performance FPGA, low power, high performance, and high power, low performance. Like different FPGAs are quite classified. Anyway, I will go to the overview of the high-end overview. It's a low range FPGAs, which is caters to the 20 nanometer technology, and high range FPGAs. That's another FPGA, that's medium range FPGAs that caters to 30 nanometer technology and high range FPGA. These are the different classification FPGA where the customers finds enormous applications to drive their market. The syntax and elaborating is technology mapping optimization. So we have a technology library like 5 nanometer, 7 nanometer. That technology library has to be mapped and then go for optimization. So that is we call as a synthesis. Then we go to the functional verifications, and then the design implementation. So before in the FPGA process, we have a synthesis that in the synthesis, we have an input-output planning where we stick the pins of the design oriented, the input-output pins, and that is to a banking voltages. That is like the input-output planning. And then we go for the it's in the constraints and timing constraints, which normally we need to define these current clocks, generated clocks, input delays, output delays, virtual clocks, as well as the exceptions like false path and multi-cycle path. These are the quite tricky part. You need to work for the FPGA and the timing constraints thing. This, okay. Then you have to generate after synthesis. Then you have to go for floor planning. Then your placement and routing. The tool will do, or the manual routing can be done. You can see the real estate of the FPGA when you open a synthesis, any FPGA synthesis tool, or any whether the devices provide like Xilinx or any vendors or Intel provides. You can see the floor planning, placement, and routing mechanisms that the tool performance. And so there are many concepts behind it. So what's the objective of this floor planning? So the objective of the planning, placing the logics across and how to route it. There will be quite a routing congestion will be there, how to avoid, how to achieve a better optimization strategy. Even the tool provides some certain strategies. Even you should be very intelligent to pick those and using your flow. And finally, you have different types of flash programming methods in FPGA. You have JTAG, SPA flash, are there. Normally, after the synthesis, and when you download the image bit file on the FPGA board, and we used to take validate, or we can take as well as the verification side. We can go for checking the hyperterminal, or we can use the now in recent times we use word HLS, where CC libraries are being used. Here the application library talk to the kernel. Like this, you can go for a very efficient debugging. This is a quick on the design flow. So there are quite a challenges in chip design flows. When you talk on the system on chip, different IPs contributions, and like UART, I2C, CSP, and high-speed protocol like PCI, USB, Ethernet also. So that depends upon the customer how it is bringing up the chip. The cost of chip is quite $1 million to $100 billion. There's quite complexity and a lot of technology involved in it. So when the customer is going from the very sophisticated optimization technology like 7 nanometer, 5 nanometer technology, also even though for mobile application, for example, for IoT applications, that will be less technology, which is 25 nanometer or 45 nanometer. That depends. There are quite a sophisticated language, as you know, that system Verilog VHL is being used. There is a global team to deploy to various time zones, and there are different hierarchies that are available as a pyramid team structures also. The major contributors for the team cost, the EDA tools involved around this the ecosystem, and different IPs that going to support that SOC. So the actual chip cost, normally when you see the cost in million, minimum will be the cost maximum. You have your engineering, design engineering cost, and you have your firmware cost, you have your packaging cost to build as a product, a SOC environment, and you have an EDA tool, EDA infrastructure cost, and finally when you come to the RTL to GDS2, and the GDS2 format is needs to be made to the fab, across the fab. You need to have a tap out, and we often post silicon validation testing on a lot of things, and that build up the costs. Okay, and these are the open source. This open source come to the rescue because of the high cost in building the EDA infra, the tool license. So we found that the open source can help the industry, academics, keeping the EDA tool infrastructure for the community to grow as industry collaboration within academics, or as a even for hobbyists, it's very quite important. So building missing pieces in course, you can contribute to them, build a talent, attract the talent community. You can improve the ecosystem. There's a continuous integration, continuous deployment of integration practices growing across the world for the open source environment. there's a potential is quite high, is quite boomed up, and a diversified workforce skill is there for the EDA tool industry. Um, so that's a key point of the discussion. Is that why open source? Why people who works on open source? Why the world is moving towards the open source? So you can build your own linter, you can build your own synthesis tool, and through the open source, you can able to modify through the different scripts like Python, like different. The Python is the biggest uh, tool that is spoken in the real world. So everyone tells Python, the Python is a bus. So automation is the bus. World is going to the automation. So a lot of resources, timing can be saved by when you pick up the automation as a tool. That's only the open source where it stands. It's quite scalable. Actually, it's a modular one. So yours is a synthesis tool normally we call us. It's quite helpful for optimization, mapping, everything. So normally we go for Verilog system, Verilog or VHL to gate level netlist. It quite supports FPGA, SIG, and flows, Xilinx, lattice, high water PDK. That quite salient features we have, the technology mapping, how it maps to the compile and elaborate maps to the technology, certain technology library, go for optimization, right? And go for formal verification. There's a different plugins are available. There's scripts and Python. There's quite modular that can the customer can able to play around. There's a popular in open source hardware. The risk. So for five users, open hardware, open Titan. They also use the formal verification support with SMT libs as well as Eiger support. Export is there. The predominant and tremendous exploitation in industry resources and education. So when you see anywhere, then you can see open source tool infrastructure, such as a open tool full flows like a Silicon compiler or an open source open road initiatives on the boom. So why Oasis? Oasis is such a synthesis tool of over. However, when we speak on when I compare with my Xilinx or your Intel tool like Cortex, that reward is too big because of a lot of unused stuffs inside and quite big. So when you see the Cortex on the other hand, it occupies 29 to 36 gigabits of disk space depending on the operating system. The device support because additional 3 to 36 gigabytes of disk space depends upon your device family, which is chosen. These are the things such as user friendly, that customized, users can plug and play, then plug and play with your automation. That's bugs are being minimal. So widely accepted across academic and industry collaboration or consortium. It's a trusted in ASIC and FPGA flows when we go for prototyping to production. It's a plug-in architecture. It can allow for a wide extension and optimizations to fit to the customer project needs. So our next topic is on the lint. Why lint? Lint is often used in software also to reduce the bugs. The lint helps the tools, the synthesis tools, because more time cannot be spent on the synthesis tool. Thus, the time and resources can be saved, money can be saved, and Lint has certain coding guidelines that the coding guidelines are given by the customers. The customers may be in aerospace, automotive, defense, space, consumer applications, or industrial equipment applications. This tool integrates with the continuous integration and continuous deployment. The linters are quite needed. They have a certain coding guidelines. Some of the coding guidelines I may tell there's a multi-driver issues and latch rules, right? Then how to use this blocking, unblocking statements, mixed use of blocking, and what does it mean for? So these guidelines are totally affected by the recommendation of the customers. That's I told about different domains, uh, uh, different verticals like uh, aerospace or defense, space, industrial equipment, consumer, like that. So the linters are quite needed industry for system Verilog and system Verilog test bench, system Verilog RTL and UVM assertions, accelerations, emulations, and formal verifications. Right. So when you miss the lint, you will get n number of issues. When you see from the design side, 1x, and the static analysis points x times x, integration testing 15x. Oh, the customers in the field gets quite messy on the this 100x. How can you deploy this? So you should be very much aware of the lint mechanisms and the lint coding guidelines, how to feed into the lint tools. So the lint, yeah, the open source market is quite helping the industry and the academia for the lint tool. So the primary objective is how the FPGA, where the lint is being used and how to effectively utilize the resources. I mean, the lookup table, the system Verilog RTL design constructs. That is my subset. That is a type def, a logic enumeration structure package interface always underscore FF always combinational sets and streaming operators dollar based dollar signs. These are the quite rolling out that operator enhancements, the packed arrays, the arrays are sports in name of enumeration, literal enhancements, the structure, package casting, interface, wildcard and name ports, as well as sets and the string operators in the case of dollar based and dollars, right? The coming generations BioLint approach. That's a BioLint is built upon the Python scripts. The Python give Python-based rules on PySlang. So these are the minimum rules available space on the right hand side. You can see that how the BioLint is get declined and approach. As I said that every customers across the semiconductor domains, they can give the rules proprietary and you can go for customizing those rules. And there's a newer applications and it's not intended a traditional EDA product. It opens room for innovations, but rather than open room for innovations now, it's a solid data model. It's like similar to the Verilog VPI object model, not a fancy graph or set or pattern matching. This is for the checking for the bugs before you go to the synthesis. So violent in action, you can see the violent violation system develop parameter that is not supporting YASIS, and you can see what's the violation end labeling checker. When you run the tool, right, you can see the syntax error, unexpected things out there. You can when you see the inside the test folder on synthesis test, you have the test underscore. This is captured from my work, which when we're working on the lint. There's a logic underscore parameter as well as for the enumerations and the two array ports and all. So this is some of the violations I am bringing up in this. I'm pulling from this to the slides. So this is violations. That's no portion checker and not supporting OS. So some of the things are not supporting OS. There's a no ports and here when you see some of the things are not supporting. When you see the right side, we have the unexpected syntax error. So now I'm moving to the FPGA. As a designer, what we do, you have to follow this coding guidelines strictly. The synthesis will coding guidelines, lint rules that's recommended by the customer, and you can able to the customer can revisit the rules to get the minimal optimization, and we can tell the resource utilization of the LED should be less. Efficient utilization of LED should be there. So we need to go for combining different or you have to select the Verla coding guidelines. When you combine on multiple conditional statements, so it may go for a complex design that's a nested if else and cascaded that is to handle multiple conditions. So nested if statements and allow use for additional conditions if or else block of another or another conditional statements. So nested if statements. So that is a thing we are bringing up here. So optimization, just a heads up on this in lookup table. The constraints are needed. Optimization from FPGA. Here we go on speaking of the LUTs and DSP slices and block ramps. It handles specific constraints such as LUTs, DSP slices, and block ramps. So LUT lookup table is provide a fast and more predictable performance one. So lookup table is a twist. Normally, basic is a twist of an AND gate, like uh, you can take like this one, or the internal routing and interconnects are quite optimized. When you pull up the synthesis tool, right, you can able to see that synthesis the routing and see physically there in the real estate of the FPGA. These are quite optimized and that there's retrieving the data from the LUTs, which ensure the quite the rapid function of logic function. Okay. And this so this CLBs, carry chains, multiple. So multiplexer is logic gates. Multiplex is one of the basic building blocks of FPGA. So the LUTs can be time multiplexed to implement algorithms or multiple logic functions with a single lookup table. Our approach is to maximize the resource. This LUT's approach is to maximize the resource utilization and optimize this overall design. So this is some of the basics of the LUTs. Now we will go through nested if else statement in FPGA LUTs. So the consideration should be effective usage of resource. Effective resource means an LUT, or we can call as a minimization of LUTs. This is a key goal for designers. Nested structures that create more complex logic that can be mapped to LUTs. So larger blocks are quite resource intensive and resource potentials. Then there are other scenarios when certain conditions are going for a don't care like things. So I may go for a small piece of code. This is a comparator, and you can see this comparator right hand side is a schematic one, and I have A and B, right? 3 down to 0. I'm taking a number of 4 bit on one and B equal to 4 bit 000 all. So I am defining my conditions A greater than B. Okay. And A equal to 1. And A is greater than B and not of A equal to 1. And another conditions I have A is less than B and B and A is less than B, B not. And another condition A equal to B. So this here the default is important. The latches are inferred. So I may go for a default conditions. So this is one of the lynch. Okay. So impact of resetting the flops. So resetting the flops means in FPGA that they going to improve the FPGA performance. It can diminish the congestion and by resetting all the flops with the data values. So you need to sample the data path when the control path is indicates the data is valid. So when you have a selective mechanisms, right, we go for avoiding this unnecessary utilization of LUT, and you can focus the research on quite relevant flip-flops. What the flip-flops are quite needed. So one design style that the reset, that's only the want the flops that can hold the valid signals. Controlled approach when the resets are applied, quite diminishing the routing congestions and quite optimizing the timing without the necessary, without the unnecessary LUTs. I mean that uh, it can able to help the FPGA designer for a effective LUT utilization. So we can apply with the uh, we can play with the LUTs. That is quite necessary. That's the meaning for that saying. So I also pull up another code which is a data valid generator. We can tell. So if reset, the valid is zero. Else the data is the one. And right hand side you can see the schematic of that one. Okay. And this is like a I go for a cipher test. There's a security thing. That's if valid, you need to rotate the data and you need to add the offset. And else you go for holding the previous valid, not valid. So I'll go for uh, data out equal to register. I have to output that one. So this is the one thing actually. So the BioLint identifies the system error rules enumerations as I told. I'm repeating the same thing, the enumeration inside the modules, such as in the signals and the multidimensional arrays, type depths, packages, string operators, like uh, like the simples, the inside operator in case, inside statements, the node port declarations interfaces. Build your own linter. They're exciting new frontiers in and the EDA tool infrastructure. Open resources can lead the way for the commercial tools. Faster turnaround, wide number of players, wide number of operators. I mean, the operators in the sense of developers who can help the industry and academic try to innovate. What linters you can build on top? You can think it's quite an innovation. So yeah, thanks AsFigo and Verifox for proceeding it, for keeping me on the index. Thank you very much. System Verilog linter for users. Please visit us. Thank you.